Here we are going to talk about directional derivatives. Directional derivatives. Okay? The directional derivative of phi, which is a scalar function or a scalar field, in the direction of a unit vector is this. The phi ds is equal to the dot product of the unit vector and the gradient of phi. This is the formula for directional derivative. The phi dx equal to the unit vector a, that is the dot product of the unit vector a and the gradient of phi. You can say the phi ds equal the dot product of the unit vector a and the gradient of phi. We are to determine the directional derivative of this function at the point in the direction of this vector. So what we need for directional derivative, phi dx, is the unit vector and the gradient of the scalar field. Now, remember the formula for unit vector. If I have a vector A equal to AI plus BJ plus CK, the unit vector in the direction of A, written as this, okay, is equal to the vector itself divided by the modulus of the vector A, okay, that is the modulus of A. And the modulus of A itself is this, the square root of A squared, that's this, plus B squared plus C squared. So the unit vector, okay, is equal to AI plus BJ plus CK divided by the magnitude of the vector. So we need the modulus of this vector and the grad of this scalar field. Okay, let's solve. First of all, let's determine the grad of phi. Okay, remember in the previous video I talked about the gradient of the scalar field, and we've said that grad of phi, which is equal to this, is the partial derivative of phi with respect to x times I plus partial phi partial y times j plus partial phi partial z times k. Okay, so let's go ahead. The grad of phi will be equal to this. What is the derivative of this function with respect to x? That means we are going to keep y and z constant. So let's differentiate this now with respect to s, keeping y and z constant. Okay, so let's differentiate this first one, s square y. To keep y as a constant, differentiate s squared with respect to x to get 2x. Let's differentiate this now, minus 2x z squared. Keep z minus 2z squared as a constant. Differentiate x with respect to x to get 1. Since there is no x here, it means that this is a constant. And so the derivative of this constant is equal to 0. So that's out. That means partial phi partial x is equal to this times I. This is the I. Plus, let's determine partial phi partial y. We differentiate this again with respect to y now. So keep s squared as a constant. Differentiate y with respect to y to get 1. Keep, okay, there is no y here. That means the derivative becomes 0. Since it is a constant, there is no y in this expression. So we have 0. Keep z as a constant. That means we are differentiating this now with respect to y. We are keeping z as a constant. Differentiate y squared with respect to y to get 2y times j. Now, plus, let's differentiate this function now with respect to z. So there is no z here, it becomes 0. Okay, we keep minus 2x as a constant. Differentiate z squared with respect to z to get 2z. We keep y squared as a constant and differentiate this to get 1. So the gradient of the scalar field as the gradient of I is equal to this. This is 2xy minus 2z squared. Okay, times I. This is x squared plus 2yz times j. So we have minus 4xz plus y squared. Minus 4xz plus y squared times what? K. So this is the vector function. Okay, remember we said that the grad operator will act on a scalar field to produce a vector. So at the point 1, 3, 2, 1, comma 3, comma 2, the grad of phi is equal to this. X is 1, y is 3, and z is 2. So 1 times 3 is 3, times 2 is 6. So we have 6 minus z squared, that will be 2 squared, and 2 squared is 4. 4 times 2 is 8, plus s is 1, so 1 squared is 1, y is 3, z is 2. 3 times 2 is 6, 6 times 2 is 12. Alright, I hope you are following. X is 1, z is 2. So 1 times 2 is 2, times minus 4 is minus 8. Then y squared, which is 3 squared, is 9. So plus 9 times k. So finally, what is grad of phi? The grad of phi will be equal to this. Okay, 6 minus 8 is minus 2, so we have minus 2i. 1 plus 12 is 13, 13j. Okay, minus 8 plus 9 is 1, so times k, that's k. So this is the gradient of the scalar field at this point. Okay, let's keep this somewhere. Let me just put it here. We said the grad of phi is equal to minus 2i plus 13j plus k. Good, so what is left now is the unit vector. Okay, the unit vector A. Let's determine that here. So the unit vector in the direction of A, this is the vector A now. We need the magnitude of the vector. So the magnitude of the vector A, or the modulus, or the length of this vector, is the positive square root of 3 squared plus 2 squared plus minus 1 squared. Minus 1 is the coefficient of k there. This is 9, 4, 1. 9 plus 4 plus 1, and that's 14. So the unit vector in the direction of A is this. The vector itself, which is this, 3i plus 2j minus k, divided by what? The modulus of the vector A, which is root 14, so root 14. And this is equal to 3i over root 14 plus 2j upon root 14 minus k upon root 14. We can now determine the directional derivative, d phi dx. The phi dx is equal to the dot product of this and this. Already there's a video for unit vector and there's a video for dot product, triple product as well. So you can watch to learn how to determine dot products, unit vectors, and so on and so forth. So the unit vector is this. 3i over root 14 plus 2j upon root 14 minus k over root 14 dot minus 2i plus 13j plus k. For dot product, we are going to multiply the corresponding coefficients of I, j, and k respectively. So we have 3 over root 14 times what? Minus 2 plus 2 over root 14 times 13 plus minus 1 over root 14, which is the coefficient of k there, times what? 1. So what is this equal to? The directional derivative defined here in direction of the unit vector is equal to this. This is minus 6 upon root 14. This is what? Plus 2 times this is 26. Okay, this is minus 1 upon root 14. Since the denominator is common, just say 1 upon root 14, then evaluate their numerator. Minus 6 plus 26 minus 1. Okay, so we have this 1 upon root 14 into minus 6 plus 26 is 26 minus 6, which is equal to 20. 20 minus 1 is 19. So this is equal to what? 19 upon root 14. 5.077963 and so on and so forth. So if I approximate this to, let's say, 3 decimal places. So 3 decimal places we have 5.078. Okay, so we have 5.078. So 3 decimal places. So this is how to determine directional derivative. Okay, directional derivative. I hope you enjoyed the video. Subscribe, like, and share this video to your friends and to your classmates.